Today I'm going to be talking about a variety of statistical assumptions. The first one will be about homogeneity. So, talking about homogeneity, when you are testing assumptions for statistics and you have more than one variable, as you would in any statistical analysis beyond descriptive data, and you're looking at two variables together, one of the assumptions is that you have equal variance or homogeneous variance in your two variables that are together. So this could be homogeneity of variance, which includes one categorical variable with a continuous variable. So for instance, any ANOVA, type of ANOVA, would have categorical independent variables and continuous dependent variable. And so you would need to check for homogeneity of variance with those type. However, also if you have two or more continuous variables, like you would have in a regression, you need to check for something called homoscedasticity. Nice big word, can impress your family with your new big word. And the assumption for both of these is that you have an equal distribution of your data at each level of your data, that it's not clumped together. So, what does homogeneity mean in terms of statistics? You might know the term homogeneous from milk. So looking at this, we have chunky milk. I don't personally want chunky milk. It's not a good thing to have chunky milk. I want my milk to be homogeneous. I want it to be exactly the same from the top to the bottom. I don't want a bunch of cream on top. I want it to be all the same, right? So I'm a Westerner, right? And I'm used to grocery store milk. That's homogeneous. So in the same way, when we are doing statistics, we don't want chunky data. We don't want the variance between different groups or at different levels to be different. We want it to all be the same. And that's one of the assumptions in doing statistics. So you could examine a whole lot of stem and leaf plots or box plots to kind of get a sense of the distribution of your continuous variable at each level of your categorical variable when you're looking at that. But there is a better way to do that. So remember that the assumption of homogeneity of variance, what you're looking at is a categorical variable on a continuous variable. So the two of those together. And the variability in scores for one categorical variable is roughly the same at every level, right? So if you're comparing freshmen versus seniors or something like that, then you want the distribution of freshmen and the distribution of seniors to be about the same. Even if their mean scores are different, that's not what we're talking about. We're talking about variance. Variance is how spread out, how varied the data is from each other, right? So you want the spread of your curve to be the same. You don't want one to be all spread out big and the other one to be really, really tight. If you're comparing two groups or three groups or four groups or however many that you're looking at, so the population variance from groups is assumed to be equal in the population. So your sample that you collected from with your participants should show that characteristic. We examine that with various statistics. The default in SPSS is called Levene's test, and there's lots of conversations about whether or not that is the best test, or whether maybe Fmax is actually better, or Bartlett's test might be better. But SPSS does Levene's test, so instead of having to train you all to hand calculate things or go to other statistics with other statistical programs, which we are not learning in this class, we are going to stick with Levene's test. But just be aware, you may run across somebody in your life who says, oh, Levene's test, that's not so great. And yes, I agree, it may not be the best one in all data and all situations, but we're going to work with it, and it's good. It's good enough. So what you're looking at here is homogeneous variance with a two-group independent variable and then a continuous variable. So let me just orient you to it. Here we have two groups. We have men on this side, right, which is comparing on gender, let's say. And we just have men and women in this sample. So we have men on this side, right, and women on this side. And these little dots are each individual person's score on religious commitment. So down here at the bottom would be like low religious commitment, right, score, and up here at the top would be the highest religious commitment score, right? And what you see here is you have a distribution that's large, right? It's going from all the way at the bottom, all the way at the top. Maybe you have a little bit more in the middle, right? But overall, you're getting a distribution. And on this one, similar. It's a big distribution. Again, a little bit more maybe in some different places, but overall, you're really in good shape. This would be homogeneous variance. So this picture is getting you a sense of what heterogeneous variance might look like in a picture. So if you have one group here, this is the women, say, and they range way out, right? And they're kind of all scattered out, meaning what you're seeing here is a very large variance, right? It's a large number. And variance is going to look at like how far spread out the data is. And this other group, which in our last one was men, it's kind of all clustered together in the middle, right? So if this was a bell curve, it would be like right like that and you'd be done. Whereas this one, if it was a bell curve, it's probably going to go like, let me get, if I can hold this, here we go, like that, right? Really big. And this bell curve is going to be really little, like that. And so what you see here is a large variance in one group and a small variance in the other group, and that's a problem. And at some point, the two variances are different enough that they're statistically significant, right? And that's bad. So what we were talking about in the last slides was categorical and continuous variables together. Now we're going to talk about what if you have all continuous variables, two continuous variables together. Can you have a problem with homoscedasticity there? Yes, you can. And homoscedasticity would be the proper term for this. This is when the variables and scores for one continuous variables, they are assumed to be roughly the same at all values of the other variable. And I'll show a picture in a minute that might help with that. You detect this by examining bivariate scatter plots, and you want blimps. So blimps make you happy here. You're going to be glad to see a blimp. You do not want to see a fan, right? Right? You got a sad face if you have a fan of data. Okay, so here we have a nice homoscedasticity, exactly what we want. What we have here is something you can draw a nice line down and everything's not too far from the line. Or if we drew a circle around it, we'd see something that looks like a blimp or a hot dog, right? And to orient you, what we have are two continuous variables, charitable giving down here and religiosity up here. You may notice that this is very similar to the assumption of linearity that we covered in a previous week, because the assumption is that you can draw a line down the middle and it's not curved, right? It's straight down. But homoscedasticity, it's assuming that at every point down this line, right? So at this point, the spread is about the same as at this point, that the spread is about the same as at this point, and the spread is about the same. And at this point, the spread is about the same, right? So at every point along this variable, the spread of religiosity, or the second continuous variable, is similar. In contrast, this would be heteroscedasticity. And what you see here is something that looks more like a fan of data, right? You can see a fan of data instead of a blimp. And so in this one, when you're at low values, you have very small variance, real little, it's really little, gets a little bigger here. And then all of a sudden it gets really big, right? So the variance when you get to higher levels of charitable giving varies widely on religiosity and creates something that can't be predicted and runs counter to the assumptions of a data set. So if you see something on a scatter plot that looks like a fan, you're unhappy. So if you're testing all your assumptions, one of the things you can do is run a scatter plot. And here you are looking for something that looks like a blimp or a hot dog. You don't want fans, you don't want rainbows, you don't want smiles, right? And you don't want hills. What you want is a nice blimp. And then you've covered both of these assumptions together. So if you look in your textbook in Mertler and Vanetta at figure 3.30, what you'll see is a test for homoscedasticity with continuous variables. That's a scatterplot matrix, and it's actually got 6 different scatterplots in a big picture. One of the things that students repeatedly tell me is they start to look at these pictures and they go, it looks like a big blob of data. I don't know. Is that a fan? Is that not a fan? When is a fan a problem? It's pretty subjective because it's a graph and you're just evaluating your graph. So just to know that using scatterplot matrices is not really used that often in like serious statistics. It's not really a gold star. But what you do want to see when you're looking at it is that hot dog, ellipse, blimp kind of look. In our labs, we do this because other analysis to test for homoscedasticity with all continuous variable is both difficult, and many people argue that it's actually not necessary for most data sets, that once you meet the assumptions of normality and linearity, that homoscedasticity, when you have multiple continuous variables, is not really necessary anymore. And there's probably good argument for that. So just kind of letting you know that you do want to look for it and examine it, and if you have that fan of data, then you start going, oh, that's too bad. But do check and make sure, did I check my normality? Because if you had a normality problem and you fixed it, you probably won't be finding problems with heteroscedasticity. So just to be aware. So just checking that you understand this concept so far. Homogeneity of variance involves what? Right? And what you're looking at is one continuous and one categorical variable. It actually can handle a little bit more than that, but in general, it's going to be one categorical variable looking at a single continuous variable. So you're looking at bivariate data overall for homogeneity of variance. For homoscedasticity, what are you looking at for that? This is all continuous bivariate level data. Okay? So just making sure that you have that straight in your head as we work through all these assumptions. And a quick understanding as to why it's a problem if things are heterogeneous in both heterogeneity of variance or at heteroscedasticity. The problem is that if that problem exists, it wasn't detected and fixed, then you end up with a higher chance of type 1 error, which inflates your type 1 error. And remember that type 1 error is a false claim, or to use kind of old statistical language, rejecting the null hypothesis when it was actually true. You don't want to make a false claim in any data, right? So you always want to make sure you have that. In contrast, failure to detect is type 2 error. But if things are heterogeneous, then you inflate the chances of a type 1 error. So that's the reason why we don't want to have this. Okay, so what do you do if you find out you have a heterogeneity problem? All right, one, just like in your ethics class, which I believe in our program, you guys are taking ethics at the same semester. The answer to everything in ethics is consult, and the answer to everything in statistics, when there's not an easy solution that your textbook gives you, is consult. So you consult your dissertation chair, or you consult a statistician. I'm here, you can consult with me, and check it out. So one thing some people do is they change their p-value to be something more strict, because if it inflates type 1 error, then if you constrict or make your p-value more strict than 0.05, then you kind of counterbalance that, right? Some people do data transformations, like we talked about earlier with logarithms and square roots. However, there are problems with that, and there's a lot of discussion about that. So just be aware that you may inflate your type 1 error, and it may just be a ding in your study. It might be just a problem in your study that you're going to report. Repeatedly in my class, that's what'll happen, is I'll ask you to just report it and say, this creates a limitation, or future data should be viewed circumspectly, things like that, particularly if it looks like you could potentially have a type 1 error. So to conclude our work in homoscedasticity, what is homogeneity and why is it important in statistics? It is that there is equal variance or equal spread of your data for multiple variables that are put together. right? When you have a categorical variable with a continuous variable, like you find in ANOVA, it is homogeneity of variance is what it's called, and you test it with something called Levene's test. If you have all continuous variables in your analysis, it is called homogeneity of variance or homogeneity, and you're going to look at scatter plots. You want to see things that are the same or homogeneous. Significant in this area is sad. So if your Levene's test is significant, then you're going to not, that means you violated the assumption. So significant is sad in assumption land, right? When things are not the same. Good job.